There was a moment, a single, unfathomable instant, when the universe woke up. Picture this, an endless sea of darkness, not a single star to pierce the void, no galaxies spiraling in the distance. Just silence, pure, absolute stillness, and then light, not the gentle glow of a sunrise, but the first flicker of existence itself, a spark that would set the cosmos ablaze with billions of suns. This is the story we're about to uncover, the unseen drama beneath that first light, the hidden forces that sculpted the universe as we know it. Think about everything around you, the screen you're watching, the air you're breathing, even the atoms in your own body. All of it traces back to that primordial dawn, a time so distant, so alien, it defies imagination. But here's the astonishing part. We've found ways to peer back into that darkness. Scientists, armed with telescopes that act like time machines, have caught whispers of that ancient light, echoes of the universe's first breath, and what they've discovered is more incredible than fiction. This isn't just a tale of cosmic history, it's a puzzle with pieces still missing. What triggered that first flash of light? What invisible hands shaped the infant universe, molding it into the galaxies and stars we see today? And how does this ancient story connect to you right now in ways you might not expect? That's the journey we're embarking on today, a voyage to the edge of time itself, where the answers lie buried in the faintest signals from the past. By the end, you won't just understand the science, you'll feel it, the awe, the wonder, the humbling scale of a story 13.8 billion years in the making. So let's begin. The universe is waiting. Imagine a universe so dark, so empty, that not a single star had yet been born. For hundreds of millions of years after the Big Bang, space was filled with nothing but a thick, silent fog, a swirling sea of hydrogen and helium, the simplest building blocks of existence. This was the cosmic dark ages, an era when the entire cosmos was cloaked in shadow, waiting for something to ignite the spark of creation. But darkness doesn't last forever. Even in that endless night, tiny ripples were forming, imperceptible at first, like whispers in a storm. Gravity, the universe's quiet architect, was at work. It tugged gently at those clouds of gas, pulling them closer, denser, hotter, and as these pockets of matter grew, they began to collapse under their own weight. The pressure built, atoms smashed together, and deep in those cosmic nurseries, temperatures soared to unimaginable heights. Then, finally, the darkness shattered. What ended this ancient night wasn't some grand explosion, but a fragile dance between two opposing forces, gravity's relentless pull and the universe's unstoppable expansion. For stars to be born, gravity had to win just long enough to compress matter until it ignited. But here's the twist. If the universe had expanded too fast, those first stars might never have formed. Too slow, and everything could have collapsed back into chaos. It was a cosmic tightrope walk, and we're here because the balance was perfect. Today, we catch glimpses of that pivotal moment in the faint afterglow of the first light. A signal so fragile it's like trying to hear a whisper across 13.8 billion years. Yet in that whisper lies the story of how darkness gave way to dawn, how emptiness became everything, and the most astonishing part, you're made of the very atoms that once swirled in that primordial fog. Proof that the universe's greatest magic trick was turning nothing into something, and something into us. Those first stars didn't just flicker to life, they set the universe on fire, not with flames but with something far more powerful. Light, ultraviolet radiation, blistering and relentless, poured from these newborn giants, and it did something extraordinary. It ripped electrons from the hydrogen atoms floating in space, a process we call reionization. Picture it like this. The cosmos had been a dense, murky fog, where light couldn't travel far without bumping into particles and scattering. But as those early stars blazed, they burned away the haze, carving out bubbles of clarity in the darkness. Slowly, then all at once, the universe became transparent, a window flung open after an eternity of shutters. But here's the mystery. How did this happen so fast? The universe is vast, and those first stars were few and far between. Yet, in what amounts to a cosmic blink, just a few 100 million years, the fog lifted. The answer might lie in the unsung heroes of this story, the earliest galaxies. Recent supercomputer simulations reveal something startling. These galaxies weren't just lone beacons, they were factories churning out stars at a ferocious rate. Their collective radiation acted like a cosmic brushfire, spreading ionization far faster than isolated stars ever could, and the key, their location. Clustered together in the densest regions of the young universe, their light overlapped, creating zones where reionization spread like wildfire. This wasn't just a change, it was a revolution. For the first time, light could travel freely across space, weaving the threads that would eventually let galaxies grow, stars form, and planets emerge. Without reionization, the universe would have stayed a shadowy prison, its potential locked away. But those early stars and galaxies, fierce and fleeting, shattered the darkness. And in doing so, they set the stage for everything that followed, including us. Because every time you look up at the night sky, you're seeing the legacy of that great awakening, the moment the universe learned how to shine. The first stars weren't just bright, they were titans, blazing with an intensity we can barely comprehend. Imagine a star not just larger than our sun, but hundreds of times more massive, a searing furnace of raw hydrogen and helium. No planets circled them, no dust clouds dimmed their glow. They burned alone in the void, their light slicing through the primordial darkness for the very first time. But what made them truly extraordinary wasn't just their size, it was their purity. These stars were pristine, untouched by the complex chemistry that fills our universe today. They were the universe's first alchemists, and their brief, fiery lives would forge the ingredients for everything to come. Inside these colossal giants, temperatures and pressures reached extremes modern stars never experienced. Hydrogen fused into helium at a staggering pace, but the real magic happened near the end of their lives. As they ran out of fuel, their cores collapsed, triggering explosions so violent they could outshine entire galaxies. In those final moments, the extreme conditions forged something entirely new. Heavier elements like carbon, oxygen, and even traces of iron. These atoms, born in the hearts of dying stars, were flung into the cosmos in explosive supernova, scattering like seeds across the universe. Here's the twist: without those first stars, life as we know it wouldn't exist. Every element essential to us, the oxygen in our lungs, the calcium in our bones, the iron in our blood, was forged in the fiery deaths of those ancient giants. They were the universe's first factories, transforming simplicity into complexity, and their legacy didn't stop there. The shock waves from their explosions compressed nearby gas clouds, triggering the birth of new stars smaller, richer in heavy elements, and capable of nurturing planets. Yet for all their brilliance, these pioneers were fleeting. Most burned out within a few million years, a blink in cosmic time. Today, we'll never see one directly. They're long gone. Their light faded into the background hum of the universe. But we've found clues. Astronomers study their descendants, stars with barely any heavy elements, as living fossils of that primordial era. And supercomputer simulations recreate their formation, revealing how gravity sculpted them from the raw materials of the early cosmos. This is the paradox of the first stars. Though they vanished eons ago, they shaped everything that followed. Their explosions wrote the recipe for planets, for life, for us. So the next time you gaze at the night sky, remember, you're not just looking at stars, you're seeing the echoes of those ancient giants, the ones who turned a universe of darkness into a canvas of light. Dark matter didn't just watch from the shadows, it built the stage where the universe's first light could shine. While ordinary matter collapsed into stars and galaxies, dark matter wove an invisible web, its gravity sculpting the cosmos on a scale we're only beginning to understand. Think of it like the framework of a cathedral, unseen but essential, holding everything in place while the stained glass, the stars, gets all the attention. Without dark matter's pull, those early clouds of gas might never have clumped together densely enough to ignite. But here's what's fascinating. Dark matter didn't just help, it called the shots. Simulations of the early universe reveal something startling. Wherever dark matter pooled most densely, galaxies followed, drawn in by its gravitational whisper. These weren't random scatterings of stars, they were precise constellations, arranged along filaments of dark matter like beads on a string, and the distribution wasn't smooth. Dark matter's uneven grip created pockets of intense star formation, while other regions remained eerily empty. This cosmic blueprint still lingers today. When we map the universe's large-scale structure, we're essentially tracing the ghostly fingerprints dark matter left behind billions of years ago. Yet for all its influence, dark matter remains frustratingly elusive. We can't see it, touch it, or even say for certain what it is. All we know is that it outweighs visible matter 5-to-1, and its gravity shaped the universe's fate. Recent studies, though, are uncovering tantalizing clues. By analyzing the faint glow of the cosmic microwave background, the afterimage of the Big Bang, scientists have spotted subtle irregularities. These tiny fluctuations might be echoes of dark matter's early interactions, moments when it collided with itself or with ordinary matter in ways we don't yet understand. The deeper we look, the stranger the story becomes. Some theories suggest dark matter wasn't entirely passive. Certain models propose it might have emitted particles or even generated heat as it moved, subtly warming the primordial gas and altering how stars formed. Others speculate that dark matter's own weather, clumps and streams moving at different speeds, could have stirred the cosmic pot, creating turbulence that accelerated galaxy growth. If true, this would mean dark matter didn't just set the table for the cosmic dawn, it seasoned the soup. One thing's certain, unlocking dark matter's secrets would rewrite our understanding of the universe's first chapters. Every galaxy, every star, every planet exists because of forces we can't yet see, and that's the ultimate irony. The story of light begins in the dark. There's a glow that fills every corner of the universe, a whisper of heat so faint you'd never notice it, yet it's the oldest light in existence. This is the cosmic microwave background, the CMB, the afterglow of the Big Bang itself. Picture it like the embers of a fire that burned 13.8 billion years ago, cooled to just a few degrees above absolute zero, but still pulsing with secrets. When we map this ancient light, we're not just looking at a snapshot of the young cosmos, we're reading its DNA. Those subtle variations in temperature, those tiny hot and cold spots. They're the blueprints for everything. The slightly denser patches became galaxies, the emptier regions stretched into cosmic voids. This is how the universe looked before it had shape, before the first stars ignited, when everything was just a simmering soup of particles and energy. But hidden within this glow is something even more extraordinary, a shadow of the first stars. As their ultraviolet light pierced the primordial fog, it interacted with hydrogen gas, leaving a faint fingerprint in the CMB's polarization. Scientists call this the cosmic dawn signal, and finding it would be like uncovering a lost chapter of history. The challenge: it's buried under layers of interference, a whisper drowned out by the static of galaxies, dust, even our own Milky Way. Detecting it would require instruments of unimaginable sensitivity, like trying to hear a single note in a symphony played across the entire sky. Yet the payoff would be staggering. This signal could tell us when the first stars switched on, how quickly they ionized the universe, even clues about the nature of dark matter. Some theories suggest dark matter particles might have subtly heated the early gas, altering how the signal appears. Others propose that exotic physics like primordial black holes or dark energy's early influence could be etched into this ancient echo. It's a time capsule waiting to be cracked open. What makes the CMB so remarkable isn't just its age, it's how it connects us to the universe's infancy. Every photon has traveled across eons to reach us, carrying stories of a time before atoms, before light could travel freely. And when we finally isolate that buried signal from the first stars, it won't just fill in a gap in our textbooks. It'll remind us that the universe's greatest mysteries aren't always written in blazing supernova or swirling galaxies. Sometimes they're hiding in the quietest glow of all. There's a cosmic radio station playing the oldest song in the universe, and we're just learning how to tune in. It broadcasts not on FM or AM, but at 21 centimeters, a wavelength so specific it's like the universe's own fingerprint. This signal comes from neutral hydrogen, the same gas that once filled the cosmos during the cosmic dark ages. Every atom of hydrogen has a tiny quirk. Its electron and proton can spin in opposite directions, and when they flip to a line, they release energy at that exact wavelength. It's a whisper from the void, a faint radio hum that's been traveling for billions of years, carrying secrets about the era before stars. But catching this signal isn't like picking up a local radio station. Imagine trying to hear a single cricket chirping in a thunderstorm. That's the challenge astronomers face. Earth's own radio noise cell towers, satellites, even Wi-Fi drowns out the cosmic signal. And it's not just our technology. The Milky Way's own radio emissions create a roaring static, while distant galaxies add their own interference. To hear the universe's first whispers, scientists have to venture to the quietest places on Earth, remote deserts, polar ice sheets, and build antennas the size of cities. The payoff, though, would be revolutionary. This 21-centimeter signal isn't just a static hum, it's a time machine. By measuring subtle shifts in its frequency, we can map how the universe evolved during its darkest chapters. If the signal appears stronger in certain spots, it reveals where hydrogen gas was clumping together, forming the seeds of the first galaxies. If it's fainter elsewhere, it might mark where the first star's radiation began ionizing the fog. It's like finding a diary from the universe's infancy, written in radio waves. Recent breakthroughs are bringing this dream closer. Projects like the Hydrogen Epoch of Reionization Array and the Future Square Kilometer Array are pushing the limits of sensitivity, using thousands of antennas to filter out noise and isolate the cosmic signal. Some teams are even sending telescopes to the far side of the moon, where Earth's radio chatter can't reach, and the results are already tantalizing, hints of a dip in the signal that might correspond to the moment the first stars flickered on. But here's the twist: the 21-centimeter line isn't just about the past. It could reveal hidden physics, like the possibility that dark matter interacted with hydrogen in ways we've never detected. Or it might expose flaws in our models of cosmic expansion, forcing us to rethink how the universe grew. Every faint pulse from the cosmic dawn isn't just a relic, it's a clue waiting to rewrite the story we thought we knew. So next time you scroll past static on a radio, remember, somewhere in that noise, the universe's oldest song is still playing. We just have to learn how to listen. Deep in the hearts of those earliest galaxies, something impossible was happening. Supermassive black holes, monsters weighing millions or even billions of times more than our sun, were already taking shape when the universe was barely a toddler. These weren't just cosmic oddities, they were engines of transformation, their insatiable hunger shaping the fate of everything around them. Picture a whirlpool in the fabric of space-time, so powerful that not even light could escape its grip. Now imagine that whirlpool spinning at the center of a newborn galaxy, spewing jets of radiation so intense they could strip electrons from atoms thousands of light years away. This wasn't destruction, it was creation. The sheer speed of their growth defies logic. How could something so massive appear so quickly? One theory suggests these black holes formed through direct collapse, a rare event where an enormous gas cloud bypassed star formation entirely, collapsing straight into a black hole under its own weight. No supernova, no fireworks, just a silent, sudden birth in the dark. Other models propose chains of violent mergers where smaller black holes smashed together over and over, building mass like snowballs rolling downhill. But here's the puzzle. Even these scenarios struggle to explain the sheer size of the supermassive black holes we've spotted in the early universe. Some were already fully grown when the cosmos was less than 700 million years old, a blink in cosmic time. Their influence on reionization might have been profound. As these black holes devoured surrounding gas, they didn't just swallow matter, they spit energy back out. Superheated disks of material called quasars blazed with the brightness of a trillion suns, their ultraviolet radiation piercing the cosmic fog like a floodlight. Some astronomers believe these quasars could have been the match that ignited reionization in certain regions, carving transparent bubbles in the hydrogen haze faster than stars alone could manage. Yet their role remains controversial. Were they the main architects of reionization, or just loud bystanders amplifying a process already underway? The answer might lie in the echoes of their light. By studying the spectra of ancient quasars, rainbows of radiation stretched by the expanding universe, scientists have found traces of partially ionized gas along their lines of sight. It's like finding charred wood around a campfire, evidence of where their radiation burned through the darkness. But there's a twist. Some of these early quasars appear shrouded in thick dust, their light dimmed. This suggests they might have formed in unusually dense environments, where galaxies collided and fed them in frenzied bursts. What's truly astonishing is how these black holes connect to the universe's larger story. The same gravity that pulled matter into galaxies also funneled gas toward their centers, feeding the beasts within. In turn, the energy they released may have stifled star formation nearby, creating a cosmic feedback loop where growth and suppression danced in delicate balance. Without these black holes, the universe might look radically different: fewer galaxies, slower evolution, perhaps even a delay in the conditions that made life possible. Yet for all their power, supermassive black holes are also cosmic mysteries. We still don't know exactly how they grew so big so fast, or why some stopped growing while others became titans. Future telescopes like the James Webb Space Telescope and the upcoming Extremely Large Telescope aim to peer even further back in time, hunting for black holes in their infancy. What they find could rewrite our understanding of the cosmic dawn, revealing whether these giants were architects of light or just witnesses to a universe waking up. One thing's certain: the story of the first light isn't just about stars. It's about the darkness too, the black holes whose gravity shaped galaxies, whose radiation pierced the void, and whose origins remain one of the greatest puzzles in the cosmos. They remind us that even in the birth of light, shadows played their part. These primordial galaxies were cosmic firecrackers, small, fierce, and blazing with newborn stars at a pace that would put modern galaxies to shame. Picture a city where skyscrapers rise in days instead of decades, where construction never stops. That's what star formation looked like in these ancient cradles of light. While today's galaxies like the Milky Way might produce 1 or 2 new stars each year, some of these early powerhouses churned out hundreds, even thousands, in the same time. Their brilliance wasn't just raw power, it was urgency. The universe was young, resources were plentiful, and gravity hadn't yet spread matter thin across vast cosmic distances. But their small size is what makes them so surprising. The James Webb Space Telescope has spotted galaxies from this era no larger than a 20th of the Milky Way, yet shining with the intensity of giants. How could something so compact produce so much light? The answer lies in their chaos. Unlike modern galaxies, where star formation is orderly and spread out, these early systems were turbulent cauldrons. Gas clouds collided, compressed, and ignited in frantic bursts, with no spiral arms or quiet corners to slow things down. Every pocket of dense material became a stellar nursery, and without heavy elements to cool the gas efficiently, stars formed in rapid, violent waves. What's truly groundbreaking is how these galaxies defy expectations. For decades, simulations suggested the first galaxies should have grown slowly, taking billions of years to reach maturity. But Webb's infrared eyes have revealed a different story, one where galaxies assembled at breakneck speed, some fully formed when the universe was less than 500 million years old. This isn't just a tweak to the models, it's a revolution. If galaxies matured this quickly, it implies that gravity worked faster in the early cosmos, or that dark matter's scaffolding was more efficient at funneling gas into these tiny, luminous knots. And then there's the puzzle of their light. Spectra from these ancient galaxies show something unexpected. Heavy elements like oxygen and carbon, forged in the hearts of the first stars, were already present in surprising amounts. This suggests that generations of stars lived and died in the blink of a cosmic eye, seeding their surroundings with the building blocks of planets and life far earlier than we thought. It's as if the universe hit fast forward, compressing billions of years of chemical evolution into a frenzied few hundred million. Yet for all their brilliance, these galaxies were fragile. Their furious star formation likely blew away much of their gas, leaving them vulnerable to mergers or fading into obscurity. Many may have been devoured by larger galaxies, their stars becoming the foundation for the majestic spirals we see today. Others might have burned out entirely, their light now lost to the void, but their legacy endures. Every heavy atom in your body, every speck of dust in a distant nebula traces back to these tiny titans. The most thrilling part, we're only beginning to uncover their secrets. With each new Webb observation, the early universe grows stranger, more dynamic, more alive. These galaxies aren't just relics, they're proof that the cosmos has always been a place of wild creativity, where the rules we know today were written in fire 13 billion years ago. And somewhere in their faint glow lies the answer to how darkness became light, and light became everything. The hunt for population 3 stars isn't just about finding ancient objects, it's about chasing ghosts. These mythical giants, made purely of hydrogen and helium, left no direct survivors. Their lives were too bright, too brief, ending in cataclysmic explosions before the universe had even finished its first billion years. Yet their legacy lingers in the chemistry of everything around us, like cosmic breadcrumbs leading back to the dawn of time. So where do we search for something that vanished so long ago? Astronomers have two strategies: look far or look close. The first approach pushes our telescopes to their limits, scanning the most distant galaxies for traces of these stars' fleeting glow. The James Webb Space Telescope is our best hope here, its infrared vision piercing through cosmic dust to spot galaxies so far away. Their light has traveled nearly the entire age of the universe. Within these faint smudges, we might catch population 3 stars in their final act supernova, unlike anything we've seen before, lacking the heavy elements that define modern explosions. Their light curves would be unmistakable, a signature of pure hydrogen burning at temperatures modern stars can't replicate. But there's a twist. Some theories suggest a handful of these pioneers might still exist, hiding in plain sight. The Milky Way's halo, the sparse outer region of our galaxy, could be sheltering ancient, slow-burning remnants. These wouldn't be the original massive stars, but their smaller siblings, stars that formed from the slightly polluted gas left behind after the first supernova. They'd contain just a sprinkle of heavier elements, a chemical fingerprint betraying their lineage. Projects like the Sky Mapper survey have already spotted candidates: dim, ancient stars with iron levels 10,000 times lower than our sun's. They're not pure population 3, but they're the next best thing, living fossils whispering clues about their long-dead ancestors. The real breakthrough, though, might come from an unexpected place: black holes. If population 3 stars were as massive as we think, many collapsed directly into black holes without the fireworks of a supernova. These primordial black holes, invisible but for their gravity, could still be drifting through the cosmos. Recent gravitational wave detections have hinted at mysterious, mid-sized black holes that don't fit modern formation models. Could they be the remains of the universe's first stars? What makes this search so thrilling isn't just the science, it's the stakes. Finding even one true population 3 star would rewrite our understanding of cosmic dawn, confirming theories about how light first pierced the darkness. And buried in their spectral lines might be answers to even bigger questions. How did dark matter shape their formation? Did they form alone or in clusters? Every hypothetical answer is a thread pulling us deeper into the universe's greatest origin story. So while these stars may be ghosts, they're not gone. Their atoms are in our bones, their light echoes in the cosmic microwave background, and their descendants might still flicker in the galaxy's quiet corners. The hunt isn't just about the past, it's about tracing the path that led to us. Among the universe's most puzzling signals, fast radio bursts stand out: brief, intense flashes of radio energy that last just milliseconds, yet pack the power of hundreds of millions of suns. First discovered in 2007, these bursts arrive without warning, flickering across the cosmos like cosmic Morse code. Some erupt once and vanish, others repeat at irregular intervals, defying easy explanation. But buried in their fleeting brilliance might be a clue to the early universe's most elusive era. One leading theory connects them to magnetars, super-dense, highly magnetized remnants of massive stars. When these neutron stars experience starquakes or magnetic field rearrangements, they could release torrents of energy as fast radio bursts. But here's the tantalizing twist. If magnetars formed from the deaths of the first stars, their bursts might carry echoes of that primordial environment. The earliest magnetars would have spun faster, their magnetic fields stronger, potentially creating bursts far more energetic than anything we see today. It's like comparing a lightning bolt to a candle. Both are fire, but one carries traces of a storm we can barely imagine. Yet there's another, more speculative possibility. What if some fast radio bursts aren't just products of the early universe, but relics of it, hypothetical objects like cosmic strings? defects in spacetime left over from the Big Bang could theoretically release energy as they vibrate or snap. While no direct evidence supports this, the sheer diversity of burst patterns keeps the door open for exotic explanations. After all, the universe has surprised us before. What makes these bursts so valuable isn't just their origin, it's their journey. As they travel across space, they pass through clouds of ionized gas, which subtly distort their signal. By analyzing these distortions, astronomers can map the otherwise invisible matter between galaxies, including the sparse hydrogen left over from the cosmic dawn. Some bursts even exhibit a telltale frequency sweep, a fingerprint of their passage through the intergalactic medium. In essence, each burst is a messenger, carrying news of the cosmos's hidden scaffolding. The hunt for answers is accelerating. New telescopes like the Canadian Hydrogen Intensity Mapping Experiment and the Deep Synoptic Array are scanning the skies with unprecedented precision, catching dozens of bursts each month. Already, they've traced some to distant galaxies, confirming their extragalactic origins. But the real breakthrough would be catching one from a galaxy so far away, its light dates back to the epoch of the first stars. That signal, if found, could reveal how matter was distributed in the universe's youth, offering clues about reionization or even dark matter's role. Of course, not all mysteries yield easily. Fast radio bursts might remain enigmatic for years, their true nature just out of reach. But that's the beauty of cosmic detective work. Every burst is a piece of the puzzle, a fleeting glimpse into the universe's grand narrative. Whether they're tied to the first stars or something stranger, one thing's certain: these milliseconds of radio light are rewriting the story of the cosmos, one burst at a time. Quantum fluctuations might sound like the smallest possible wrinkle in reality, but they shaped the entire universe. Picture the cosmos in its first sliver of existence, a seething, hyperactive sea of energy where particles blinked in and out of existence faster than a thought. In that chaos, tiny irregularities emerged, random blips where matter was ever so slightly denser or sparser. These imperfections were microscopic, smaller than an atom, yet they became the universe's blueprints. Without them, galaxies wouldn't exist, and neither would we. Inflation theory explains how these quantum hiccups grew to cosmic proportions. Imagine stretching a crumpled sheet of paper until it's smooth. Now picture that sheet as spacetime itself, expanding faster than light during the universe's first trillionth of a second. As it stretched, those tiny fluctuations stretched too, magnified from subatomic quirks into vast ripples spanning light years. Gravity did the rest. Over billions of years, denser regions pulled in more matter, growing into galaxies and galaxy clusters, while emptier zones became the cosmic voids we see today. But here's the catch: inflation isn't just a neat idea, it's a prediction machine. The math suggests these primordial fluctuations should follow a very specific pattern, one that leaves faint imprints in the cosmic microwave background. And when we look, the CMB's temperature variations match the theory's predictions almost perfectly. It's like finding a fossil with the exact bone structure your model said it would have. Yet mysteries linger. Why did inflation start or stop? What triggered it? Some theories propose a field called the inflaton, a kind of cosmic energy that powered this hyper-expansion before decaying into the particles we know. Others speculate about multiverses, where inflation never ends in some regions, spawning endless bubble universes with different physics. And then there's the puzzle of the fluctuations themselves. While their overall pattern fits, some anomalies defy explanation, like the cold spot in the CMB, a strangely large patch of cooler radiation that might hint at physics beyond our current understanding. What's astonishing is how these quantum fingerprints connect to us. The same fluctuations that seeded galaxies also determined where stars would form, where planets would coalesce, and ultimately where life could arise. In a very real sense, your existence traces back to those random jumps in the primordial dark. It's a humbling thought. The universe's grand structure, from the largest supercluster to the smallest atom, was written in quantum static before time had meaning. The search for answers continues. Next-generation telescopes aim to measure the polarization of the CMB with unprecedented precision, hunting for signs of primordial gravitational waves, ripples in space-time from inflation itself. Finding them would be like hearing the echo of the Big Bang's first tremor. Until then, quantum fluctuations remain one of science's greatest stories, how the smallest things built the largest. What if our universe isn't the only one, just a single bubble in an endless cosmic froth? The Multiverse Hypothesis suggests that the first light we've been chasing might not be unique at all, but one of infinite cosmic dawns, each flickering to life in its own separate reality. This isn't science fiction. It's a serious, if speculative, extension of the physics we already know. Inflation theory, which explains the universe's explosive early growth, hints that this expansion might not have stopped everywhere. Some regions could still be inflating eternally, spawning new universes like branches on an infinite tree. Each would have its own laws, its own constants, its own version of light breaking through the darkness. But here's the twist. If multiple universes exist, their very diversity could explain why ours seems so finely tuned for life. The strength of gravity, the mass of an electron, even the energy of the first light. If these values were slightly different, stars might never have formed. In a multiverse, most universes would be sterile, their physics incompatible with complexity. We'd find ourselves in one of the rare exceptions, simply because we couldn't exist anywhere else. It's a cosmic version of survivor bias, where the mere fact we're here to ponder the question shapes the answer. Critics argue this idea is untestable. If other universes are forever beyond our reach, how can we prove they exist? Yet some scientists are hunting for clues. One possibility lies in the cosmic microwave background. If our universe ever collided with another, the impact might have left a bruise in the CMB's pattern, a strange asymmetry in the afterglow. Others look for anomalies in the distribution of galaxies, or even subtle shifts in fundamental constants across space. So far, no smoking gun has been found. But the search forces us to ask deeper questions. Is the multiverse a scientific theory or a philosophical escape hatch? The real power of this idea isn't just in the science, it's in the perspective shift. If countless cosmic dawns have risen and fallen beyond our horizon, then the story we've been telling about the first light isn't just history. It's a single page in an infinite library, one where every possible beginning, middle, and end is written somewhere. That doesn't diminish our universe's wonder, it magnifies it. Every atom forged in those first stars, every photon that escaped the primordial fog, becomes part of something even grander, a tapestry of realities where light, in all its forms, keeps breaking through the dark. Whether the multiverse is real or not, it challenges us to think bigger. Our universe's first light might be special, but it doesn't have to be singular. And that's the most breathtaking possibility of all. Even with our most powerful telescopes, the universe keeps its earliest secrets locked away. This isn't just a matter of distance, it's a fundamental barrier woven into the fabric of reality itself. The cosmic microwave background, that faint glow from 380,000 years after the Big Bang, marks the edge of our observable horizon. Before that, the universe was a scorching plasma, so dense and hot that light couldn't travel freely. It's like trying to peer through a wall of fire. The farther back we look, the thicker the fog becomes. But the challenge doesn't stop there. The universe's relentless expansion stretches light from the earliest galaxies into the infrared, redshifting their signals until they're nearly undetectable. Worse still, some regions are receding so fast their light will never reach us, lost beyond the cosmic event horizon. It's as if the universe is slowly turning off its own lights, one by one, leaving vast stretches of its history forever in shadow. Yet astronomers aren't surrendering to the darkness. New tools like the James Webb Space Telescope are designed to catch those stretched, fading whispers, pushing our vision closer to the first galaxies. But to go further, we'll need more than bigger mirrors. We'll need entirely new ways of seeing. Some scientists are turning to gravitational waves, ripples in space-time from the universe's birth throes, which could carry information from epochs before light could escape. Others hunt for elusive neutrinos, ghostly particles that slipped through the primordial plasma unscathed. These cosmic messengers might hold clues from the first seconds after the Big Bang, a time no telescope will ever directly observe. The boldest ideas flirt with the limits of physics itself. Could quantum fluctuations in the early universe have left imprints on the distribution of galaxies? Might primordial black holes, forged in the first chaotic moments, reveal their presence through subtle gravitational lensing? Every unanswered question is a crack in the door, a chance to glimpse what lies beyond our current understanding. What makes this pursuit so thrilling isn't just the promise of discovery, it's the possibility of rewriting the rules. If we find evidence of cosmic inflation or detect relics from before the Big Bang, we might uncover layers of reality our current physics can't explain. The universe's first light didn't just illuminate the cosmos, it set the stage for a mystery we're still unraveling, one horizon at a time. The James Webb Space Telescope is peeling back layers of cosmic history like never before, and what it's finding is turning astronomy on its head. Galaxies so massive, so mature, they appear fully formed when the universe was less than 5% of its current age. These cosmic giants shouldn't exist under our current models, yet there they are in JWST infrared gaze, glowing with the light of billions of stars that somehow assembled at breakneck speed. It's as if we've opened a textbook only to find entire chapters missing. Their pages were written by forces we don't yet understand. Take Sears 93,316, for example, a galaxy so distant its light has traveled 13.4 billion years to reach us. Based on its size and brightness, astronomers estimate it contains stars totaling several billion times the mass of our Sun. But here's the catch: according to conventional theories, there simply wasn't enough time after the Big Bang for gravity to pull together that much material. It's like finding a skyscraper in the middle of a wilderness we thought was untouched. The implications are staggering. Either star formation in the early universe was wildly more efficient than we imagined, or something, perhaps dark matter's invisible scaffolding, accelerated galaxy growth in ways our simulations never predicted. Then there's the puzzle of their shapes. JWST razor-sharp images reveal that many early galaxies aren't the chaotic blobs we expected. Some show delicate spiral arms, others orderly disk structures that theoretically require billions of years of quiet evolution to form. Yet these galaxies achieved such sophistication in a cosmic heartbeat. One leading hypothesis suggests that turbulence in the primordial gas, stirred by supernova explosions or voracious black holes, might have jump-started their organization. But even this explanation feels incomplete, like trying to solve a jigsaw puzzle with half the pieces still hidden. The telescope's spectral data adds another layer of mystery. By splitting starlight into its component colors, JWST can detect the chemical fingerprints of distant galaxies. Astonishingly, some already show signs of heavy elements like oxygen and carbon elements forged in the hearts of stars and scattered by supernova. This means generations of stars must have lived and died in the blink of a cosmic eye, seeding their galaxies with planet-building material far earlier than anyone guessed. The universe, it seems, was in a hurry to get started. What's truly electrifying is how these discoveries are reshaping fundamental questions. Could dark matter interact with ordinary matter more strongly than we thought, funneling gas into galaxies at unprecedented rates? Did the first black holes, growing impossibly fast, provide gravitational anchors that accelerated star formation? Or is our entire timeline of cosmic dawn off by millions of years? Each new JWST observation is a breadcrumb leading deeper into the unknown. The next decade promises even greater revelations. With JWST mirrors trained on thousands more early galaxies, astronomers hope to map the universe's adolescence in unprecedented detail. Future instruments like the Nancy Grace Roman Space Telescope will widen the search, while ground-based observatories like the Extremely Large Telescope will probe these galaxies' chemistry with finer precision. Together, they'll test whether our theories need tweaking or a complete overhaul. One thing's certain, the universe's first act was far more dramatic than we ever imagined. Every flicker of starlight captured by JWST isn't just a distant glow. It's a challenge, a dare to rethink everything we know about how darkness became light. And as the data pours in, one truth becomes clear: the cosmos has been keeping secrets, and we're just beginning to hear its whispers. Supercomputers are the closest thing we have to time machines, not for visiting the past, but for rebuilding it atom by atom inside a digital universe. Picture this: scientists feed equations into a machine, equations that describe everything we know about dark matter, gravity, gas physics, and the first sparks of light. Then, with a press of a button, they hit play. The screen flickers to life, and suddenly, you're watching the cosmic dawn unfold in fast forward, galaxies igniting like fireflies in a digital void. These simulations aren't just animations, they're experiments testing whether our theories hold up when faced with the universe's greatest challenge, its own birth. But here's where things get messy. Even the most advanced simulations running on supercomputers the size of tennis courts can't perfectly recreate reality. Take star formation, for example. In the virtual cosmos, gas collapses into stars too easily, producing galaxies that are either too bright or too dim compared to what telescopes like JWST actually observe. It's like baking a cake with a recipe that's missing a secret ingredient. The result is close, but not quite right. Some scientists suspect the missing piece is feedback, the way early stars and black holes injected energy back into their surroundings, heating gas or blowing it away entirely. Others point to dark matter's quirks. Maybe it interacted with itself in ways we haven't accounted for, subtly altering how galaxies took shape. The surprises don't stop there. One groundbreaking simulation, called Thesan, recently revealed something unexpected about reionization. Instead of a slow, uniform process where light seeped through the cosmos like ink in water, the virtual universe showed patchwork bubbles of ionized gas, some growing far faster than others. This matches odd patterns in the CMB, hinting that the real cosmic dawn might have been more chaotic than we thought. Yet even Thesan has limits. It can't simulate the tiniest dwarf galaxies, those faint, elusive building blocks that might have played an outsized role in lighting up the universe. It's like trying to predict a storm's path while ignoring the raindrops. Where simulations excel, though, is in their ability to test what-if scenarios. What if dark matter was warmer, moving faster in the early universe? Models show galaxies would form later, potentially solving the mystery of JWST2 early giants. What if the first stars were less massive? Reionization might have sputtered, leaving the universe half-lit. These digital playgrounds let scientists tweak the knobs of reality, exploring alternate histories where the cosmic dawn unfolded differently. And when simulations clash with observations, as they often do, that's not failure. It's a signpost pointing toward gaps in our understanding. The biggest limitation isn't computing power, it's imagination. Simulations can only test the physics we think to include. If the early universe hid forces or particles we've never detected, no amount of processing power will reveal them. That's why astronomers treat these virtual universes not as answers, but as questions, each discrepancy a clue, each success a stepping stone. The next generation of simulations will dive deeper, incorporating finer details, from magnetic fields to cosmic rays, hoping to bridge the divide between pixels and reality. What's astonishing is how far we've come. A century ago, we didn't know galaxies existed beyond the Milky Way. Now, we're crafting digital cosmos in silicon, watching them evolve and comparing their light to the faintest glimmers from the edge of time. The simulations aren't perfect, but they're alive with possibility, a reminder that the universe's first light isn't just something we observe, it's something we can almost touch. The universe was barely 1 billion years old when the first stars ignited a chaotic, radiation-soaked era where galaxies clashed and black holes feasted. Yet in that primordial frenzy, something astonishing might have happened. Life, not as we know it, not on planets like Earth, but in pockets of cosmic calm where starlight warmed alien oceans or exotic chemistry danced in the shadows of newborn worlds. This isn't just science fiction, it's a radical solution to the Fermi paradox, the haunting question of why we haven't found other civilizations. If life could arise in the universe's violent youth, where did everyone go? Consider Earth's own story. The oldest evidence of life here dates back nearly 4 billion years, mere hundreds of millions of years after our planet formed. In cosmic terms, that's lightning fast, a blink of an eye after the molten Earth cooled. If biology took hold so quickly under Earth's early hellish conditions, why couldn't it have happened even earlier, around stars born from the ashes of the first supernova? The ingredients were there: water from icy comets, carbon forged in stellar furnaces, and energy from young, hyperactive suns. The challenge was surviving. Early life wouldn't have had it easy. The universe back then was a shooting gallery, with gamma-ray bursts sterilizing whole galaxies and supernova blasting planets with lethal radiation. But extremophiles on Earth prove life thrives in unexpected places, deep in volcanic vents, buried under glaciers, even in the crushing pressure of ocean trenches. Perhaps the first organisms huddled underground on tidally locked planets, where one side eternally faced its star, or floated in the thick atmospheres of gas giants, shielded from cosmic rays. And their chemistry might have been stranger still. Before oxygen filled Earth's skies, our ancestors relied on sulfur or iron. On an early exoplanet, life's blueprint could have been written in silicon, not carbon. The implications rewrite the Fermi paradox. If civilizations arose 12 billion years ago, they'd have had a colossal head start. Some might have transcended biology, becoming post-singularity intelligences we wouldn't recognize. Others could have succumbed to the universe's brutality, wiped out by galactic mergers, resource depletion, or their own technology. The silence we hear today wouldn't mean we're alone. It might mean we're late to the party, listening for echoes in a graveyard of ancient empires. Or perhaps we're missing the signs. Alien technology from that era wouldn't look like sci-fi's gleaming cities. It might resemble self-replicating probes made of neutron star matter, or Dyson swarms harvesting energy from long-dead stars. These wouldn't broadcast radio waves, they'd manipulate spacetime itself, leaving traces in gravitational waves or dark matter distributions. our telescopes aren't designed to spot relics of a civilization that old. It's like searching for dinosaur footprints with a metal detector. The James Webb Space Telescope offers a glimmer of hope. By studying exoplanet atmospheres around ancient stars, we might detect biosignatures, not oxygen, but exotic gases like phosphine or sulfur compounds that defy natural explanations. Even a single hint would shatter our timeline of life's origins, proving the cosmos was fertile far earlier than we dreamed. This isn't just about aliens. It's about redefining life's potential. If biology could ignite in the universe's first act against all odds, then life isn't a rare accident. It's a force as fundamental as gravity or light. And that changes everything. The cosmic dawn wasn't just the birth of stars. It might have been the first whisper of a story still being written, one where life, in all its forms, is the universe's way of understanding itself. Neutrinos are the universe's ultimate ghosts. Billions pass through your body every second, leaving no trace. Born in the first second after the Big Bang, these particles carry secrets from a time before atoms, before light could travel freely. Unlike photons, which scatter off matter like ping-pong balls, neutrinos slip through entire planets as if they weren't there. Yet their near invisibility hides a surprising truth. These cosmic phantoms might have shaped the very structure of the cosmos. During the universe's first moments, neutrinos outnumbered protons by over 1 billion to 1, forming a dense, hot soup that permeated everything. As the cosmos expanded and cooled, they decoupled from matter, streaming outward at nearly the speed of light. But their exit wasn't entirely clean. Gravity, weak as it is, still tugged at them. Recent simulations suggest these fleeing neutrinos may have left faint gravitational footprints, regions where their slight mass subtly altered the distribution of dark matter and gas. Over billions of years, these tiny ripples could have amplified into the vast cosmic web we see today, with galaxies clustering along invisible filaments. It's like tracing the path of a whisper that somehow rearranged mountains. The problem, finding proof. Primordial neutrinos from the Big Bang have never been directly detected. They're too low energy compared to the neutrinos we observe from the Sun or supernova. But scientists aren't giving up. Some experiments, like Ptolemy at Princeton, aim to catch these relics by spotting the unimaginably rare moments when a neutrino bumps into an atomic nucleus. Others hunt for indirect clues in the cosmic microwave background, where neutrino-induced distortions might linger in the polarization patterns. Even a single confirmed detection would be revolutionary, offering a snapshot of the universe mere seconds old. What makes these particles so tantalizing isn't just their age, it's what they could reveal about physics itself. Neutrinos come in 3 known types, or flavors, and they oscillate between them as they travel. But some theories predict a 4th, sterile neutrino, which could interact only via gravity. If primordial neutrinos show anomalies in their behavior, it might hint at this shadowy particle, or even deeper mysteries like extra dimensions or dark radiation. Every undetected neutrino is a messenger from the cosmic dawn, carrying encrypted notes about how reality works at its most fundamental level. For now, these ghosts remain just out of reach, their stories written in a language we're still learning to read. But the hunt continues, because if we can finally trap one, it won't just fill a gap in our cosmic timeline. It'll remind us that even the most elusive particles played their part in turning darkness into light. Gravitational waves could be our only direct line to the universe's first black holes, monsters born not from dying stars, but from the raw chaos of the Big Bang itself. These primordial black holes, if they exist, would have formed when extreme density fluctuations in the infant cosmos collapsed under their own gravity. Unlike the black holes we know today, forged in supernova, these relics would carry the pristine imprint of the universe's birth, untouched by stellar evolution. And when they collide, the resulting gravitational waves would ripple across space-time like echoes from a time before light could escape the cosmic fog. Detecting these signals won't be easy. The mergers of primordial black holes would produce waves at frequencies far lower than those from modern black hole collisions, a deep hum rather than a chirp. Current observatories like LIGO aren't tuned to these ancient vibrations, but next-generation detectors like the Laser Interferometer Space Antenna LISA could change that. Slated to launch in the 2030s, LISA will float in orbit, free from Earth's seismic noise, its lasers spanning millions of kilometers to catch the faintest tremors in spacetime. If primordial black holes merged in the universe's first billion years, LISA might hear their ghostly farewell. The implications are staggering. A detection would confirm that black holes existed before stars, rewriting the timeline of cosmic dawn. Their masses could reveal the conditions of the early universe, whether it was smooth or lumpy, hot or cold in those critical first moments. Some theories even suggest these black holes could be the elusive dark matter, their collective gravity shaping galaxies without emitting light. Others propose they seeded the supermassive black holes we now find at galactic centers, growing impossibly fast by swallowing gas or merging in chains. But the real prize lies in the details. Gravitational waves encode information about their sources, the spins of the black holes, the angle of their collision, even the shape of spacetime itself in that era. A single merger from the cosmic dawn could tell us whether inflation theory is correct, or if exotic physics like extra dimensions played a role. It's like finding a fossil with a perfectly preserved heartbeat, still pulsing after 13 billion years. Of course, absence of evidence isn't evidence of absence. If LISA hears nothing, it could mean primordial black holes are rarer than predicted, or that they formed outside the detectable mass range. But silence would still speak volumes, forcing us to reconsider how structure emerged in the early universe. Either way, the hunt for these gravitational echoes isn't just about black holes. It's about decoding the universe's first whispers, written in the language of spacetime itself. Dark energy is often thought of as a latecomer to the cosmic stage, a force that only took control of the universe's expansion billions of years after the first stars flickered to life. But what if its influence began much earlier, quietly shaping the cosmos during its most formative moments? The idea that dark energy might have played a role in the cosmic dawn isn't just speculative, it's a radical twist in our understanding of how the universe grew up. Imagine the early universe as a simmering pot of possibilities, where gravity tried to pull matter together while the fabric of space itself pushed it apart. Today, dark energy dominates this tug-of-war, accelerating the expansion of everything. But some theories suggest it wasn't always a background player. In certain models, dark energy could have undergone phase transitions, sudden shifts in its behavior during the universe's infancy. These shifts might have left faint fingerprints on the distribution of matter, subtly altering where galaxies formed and how quickly they grew. It's like discovering that a sculptor's hand was guiding the clay long before the final masterpiece took shape. The evidence for this lies in the large-scale structure of the cosmos. When astronomers map the distribution of galaxies, they find a pattern that's not quite what simulations predict. There are hints of anomalies, regions where matter is clustered more or less densely than expected. Could these be echoes of dark energy's early whispers? Some researchers think so. By tweaking cosmological models to include dark energy's dynamic influence in the first billion years, they've found better matches to the observed universe. It's as if we've been trying to solve a puzzle with missing pieces, only to realize they were hiding in plain sight. But proving this isn't easy. dark energy's fingerprints would be incredibly subtle, buried under layers of cosmic evolution. One promising avenue is the cosmic microwave background. Tiny irregularities in this ancient light could carry traces of dark energy's early activity, like ripples frozen in time. Future missions like the European Space Agency's Euclid telescope aim to measure these distortions with unprecedented precision. Another clue might come from the rate of galaxy formation. If dark energy intermittently boosted or slowed the growth of structures, we might find unexpected gaps or clusters in the timeline of cosmic dawn. The implications are staggering. If dark energy was active early on, it could solve one of cosmology's biggest puzzles: why the universe's expansion rate, the Hubble constant, doesn't quite match predictions. This discrepancy, known as the Hubble tension, has divided astronomers for years. An early dark energy phase might bridge the gap, offering a way to reconcile conflicting measurements. It would mean that the force we thought was a recent player has been shaping the cosmos all along, its influence woven into the very fabric of the first light. Of course, not everyone's convinced. Skeptics argue that invoking dark energy's early role adds unnecessary complexity, that simpler explanations, like unknown properties of dark matter, could account for the anomalies. But science thrives on bold ideas, and this one has a tantalizing elegance. It suggests that the universe's story isn't divided into neat chapters, with gravity dominating early and dark energy taking over late. Instead, the narrative might be far more intertwined, with dark energy quietly nudging the plot from the very first pages. Whether this theory holds up or not, it reminds us how much we still don't know about the cosmic dawn. Every new observation, every refined simulation, peels back another layer of the universe's secrets. And if dark energy really was there at the beginning, it would mean the force that's pulling the cosmos apart today was also present at its birth, a silent architect of light and structure hiding in the shadows of time. The universe didn't have to be this way. Every fundamental constant, the strength of gravity, the mass of an electron, even the energy of that first light, could have been different. Yet here we are, in a cosmos where these values align with eerie precision to make life possible. This isn't just coincidence, it's the heart of the anthropic principle, a puzzle straddling the line between physics and philosophy. Imagine flipping a coin 1,000,000 times and getting heads every single time. You'd suspect the coin was rigged. The cosmic dawn presents us with a similar mystery, a universe seemingly rigged for life from its very first moments. Take star formation, for example. If the initial density fluctuations after the Big Bang had been slightly weaker, matter wouldn't have clumped enough to ignite stars. Stronger, and everything might have collapsed into black holes. Even the timing was critical: too early, and heavy elements wouldn't have spread; too late, and galaxies might never have formed. The cosmic dawn wasn't just a spectacle, it was a performance with impossibly precise choreography, where every step had to land perfectly for us to exist. This fine-tuning extends beyond astrophysics. The carbon in our DNA, the oxygen we breathe, these elements rely on nuclear resonances so exact that altering them by even 1% would make life impossible. Even the vacuum energy of space, which drives cosmic expansion, is calibrated to within a hair's breadth of the value needed for galaxies to form. The numbers are so improbable that some scientists compare them to a tornado assembling a fully functional jet engine from a junkyard. But why? One camp argues for a multiverse, endless parallel realities where every possible combination of constants exists, and we simply inhabit the rare universe where they align for life. Others propose deeper laws we haven't discovered yet, a kind of cosmic DNA dictating why these values had to be as they are. Then there's the controversial design interpretation, though most scientists shy from it, preferring naturalistic explanations. The anthropic principle cuts both ways. While it highlights how special our universe appears, it also cautions against assuming we're its purpose. After all, a fish might marvel at how perfectly water suits its gills without realizing oceans weren't made for fish. Similarly, we see a universe finely tuned for life because, well, we're here to see it. Any universe that didn't allow observers would, by definition, go unobserved. Yet the cosmic dawn adds a fascinating wrinkle. The conditions that birthed the first stars didn't just permit life, they actively paved the way. The violence of those early galaxies forged heavy elements, their radiation cleared the cosmic fog, their deaths seeded future generations of stars and planets. It's as if the universe wasn't just hospitable but actively constructive, turning chaos into complexity over billions of years. This doesn't answer whether the tuning was inevitable, accidental, or something beyond our current understanding. But it reshapes how we see our place in the cosmos. The same processes that lit up the universe's dark infancy also set in motion the chain of events that led to us. Whether that's destiny, luck, or one possibility among countless others remains the greatest question of all. Reionization might be the leading theory for how the universe became transparent, but it's far from the only idea on the table. Some scientists argue the process was messier, slower, or driven by forces we've barely begun to understand. Take dark matter decay, a hypothesis suggesting that if certain types of dark matter particles broke down over time, they could have released enough energy to ionize hydrogen. It's a radical departure from the star and quasar narrative, one where the invisible scaffolding of the cosmos didn't just shape galaxies but actively lit them up. Simulations show this could explain puzzling gaps in Reionization timeline, like why some regions of space seem to have cleared faster than others. Then there's the wild card of primordial black holes, these hypothetical relics from the Big Bang, some no heavier than an asteroid, might have evaporated through Hawking radiation, releasing bursts of energy that could have punched ionized bubbles in the cosmic fog. Unlike stars, these tiny black holes would have been everywhere, their collective decay acting like a cosmic-scale string of firecrackers. The math is speculative, but if future telescopes detect unexpected infrared signals or distortions in the cosmic microwave background, it could hint at their presence. Even more exotic are theories invoking extra dimensions or early dark energy. In some models, the universe's expansion wasn't perfectly smooth, brief surges of repulsive gravity, driven by unseen dimensions or shifting quantum fields, might have heated the primordial gas enough to strip electrons from hydrogen. These ideas flirt with the edges of known physics, but they're not pure fantasy. Observations of anomalous galaxy distributions or quirks in the cosmic microwave background could point to such phenomena. What keeps these debates alive isn't just imagination, it's data. The James Webb Space Telescope's discovery of overly mature early galaxies has forced researchers to revisit assumptions. If stars and quasars alone couldn't have reionized the universe fast enough, something else must have helped. Could it have been a combination of factors, a cosmic tag team where dark matter decay jump-started the process, stars accelerated it, and black holes filled in the gaps? The beauty of this scientific tussle is that every challenge to the mainstream pushes us closer to the truth, even if it means discarding old favorites. At its heart, the cosmic dawn isn't a single solved equation, it's a living conversation. Every competing theory, no matter how unconventional, is a reminder that the universe's first light might still hold surprises. And that's how science thrives, not by clinging to consensus, but by daring to ask what else could have set the darkness ablaze. We're standing on the brink of a new era in cosmic exploration, where telescopes so powerful they'll peer deeper into the past than ever before are taking shape not just on drawing boards, but in deserts, on mountaintops, and even in space. The Square Kilometer Array, or SCAR, isn't just another radio telescope. It's a sprawling network of antennas spanning 2 continents, with a combined collecting area of, you guessed it, a square kilometer. This behemoth won't just listen to the cosmos, it'll tune into the faintest whispers of hydrogen from the cosmic dawn, the same 21-centimeter signals we've been chasing, but with clarity we've never dreamed of. Imagine trying to hear a pin drop in a hurricane, and suddenly someone hands you a microphone that cancels all the noise. That's the leap SKA represents. Then there's LUVOIR, the Large UV Optical Infrared Surveyor, a space telescope concept so ambitious it makes Hubble look like a pair of binoculars. With a mirror up to 15 meters across, nearly 6 times wider than Hubble's, LUVOIR could directly image Earth-sized planets around distant stars, study the atmospheres of exoplanets for signs of life, and most thrillingly, capture the light of the universe's very first galaxies in unprecedented detail. While JWST has given us glimpses of early galaxies, LUVOIR would see them with the resolution of a modern observatory studying nearby galaxies today. It's the difference between squinting at a blurry photo and holding a high-definition portrait, but the real magic lies in what these instruments might uncover. SKA's sensitivity could finally detect the cosmic dawn signal buried in the hydrogen hum, revealing exactly when and how the first stars pierced the darkness. Did reionization happen in sudden bursts or as a slow tide of light? Were early galaxies more efficient at ionizing gas than we thought, or did something else, like those elusive population 3 stars, play a hidden role? The data could settle debates that have simmered for decades. LUVOIR, on the other hand, might catch these pioneer galaxies in the act of formation. Current telescopes see them as tiny red smudges, but LUVOIR could resolve their structures, spirals, clumps, even the faint glow of their surrounding hydrogen bubbles. It might spot the first supermassive black holes in their infancy, capturing the moment they began feasting on gas and shaping their galaxies from the inside out. And if we're lucky, it could find something even more profound. Galaxies so early, so pristine, they challenge our entire timeline of cosmic dawn. These telescopes won't just answer old questions, they'll pose new ones. What if SKA hears a hydrogen signal that doesn't match any model, hinting at unknown physics in the early universe? What if LUVOIR finds galaxies where none should exist, forcing us to rethink dark matter's role? The best discoveries often come from the surprises, the moments when the universe shrugs and says, "You haven't thought of everything." What's exhilarating isn't just the technology, but the sheer scale of the story we're piecing together. These observatories will turn faint cosmic echoes into a symphony, filling in notes we didn't know were missing. They'll remind us that the universe's first light wasn't just a moment in history, it's a beacon, still shining across time, waiting for us to learn its language. Between galaxies where darkness seems absolute lies a hidden ocean, an expanse of gas so thin, a single cubic meter might hold just one atom. Yet this intergalactic medium, often overlooked, is the universe's unsung architect. It's the fabric through which the first light traveled, the canvas on which reionization was painted, and now, with cutting-edge tools, it's becoming a time capsule of the cosmic dawn. For decades, this diffuse gas was nearly invisible to us. Unlike stars or galaxies, it doesn't blaze with light, it murmurs. But when the first stars and quasars ignited, their radiation didn't just illuminate nearby space. It etched patterns into this vast medium, ionizing hydrogen atoms and leaving behind a web of charged particles. Today, that web still lingers, and its structure holds secrets about how and when the universe woke up. The challenge, reading the patterns in this cosmic fossil. Enter quasar absorption lines, one of astronomy's most ingenious detective tools. When light from a distant quasar passes through the intergalactic medium, hydrogen gas absorbs specific wavelengths, creating dark lines in the quasar's spectrum. Each line is a barcode, revealing the density, temperature, and ionization state of the gas it passed through. By studying thousands of quasars, astronomers have stitched together a 3D map of this elusive medium, uncovering vast bubbles where reionization occurred earlier or later than expected. It's like reconstructing a forest fire spread by analyzing the charred patterns left on tree rings. But the real breakthrough comes from combining these observations with simulations. Supercomputers now model how ultraviolet light from early galaxies would have carved ionization fronts through the intergalactic medium, predicting where gas should be neutral or ionized today. When these models clash with observations like the discovery of stubborn pockets of neutral hydrogen lingering later than expected, it forces us to rethink reionization's timeline. Maybe the first galaxies were less efficient ionizers than we thought, or perhaps dark matter's distribution created cosmic shadows where light struggled to penetrate. The latest frontier, intensity mapping, a technique that sidesteps individual quasars entirely. Instead of pinpointing absorption lines, telescopes like the hydrogen epoch of reionization array measure the collective glow of hydrogen across vast swaths of sky. It's the difference between studying single raindrops and mapping an entire storm system. Already, these projects have detected large-scale patterns in the intergalactic medium's ionization, hinting at how reionization waves propagated through space. What makes this gas so compelling isn't just its role in the past, it's how it shapes the present. The intergalactic medium isn't static, it's a dynamic reservoir, funneling fresh gas into galaxies even now, fueling new generations of stars. Its structure encodes the universe's growth, from the first flickers of light to the sprawling cosmic web we see today. And as our tools grow sharper, this faint glow is becoming a portal, offering glimpses of an era when darkness gave way to dawn. The next time you look at the night sky, remember, the spaces between the stars aren't empty. They're threaded with echoes whispering the story of how the universe learned to shine. Time's arrow in the early universe seems obvious to us now. Broken eggs don't reassemble, heat never flows backward, and memories only move in one direction. But why? The laws of physics don't actually forbid time from running in reverse. Yet the universe has hurtled forward since the moment of the Big Bang, never looking back. The answer might lie in entropy, the measure of disorder in a system, and its intimate dance with the cosmic dawn. Picture the universe in its first moments, a searing, ultra-dense soup where particles were packed so tightly that everything was perfectly uniform, a state of near-zero entropy. As space expanded, matter cooled, and gravity began sculpting the first structures. That pristine order shattered into complexity. Stars ignited, galaxies spun into being, and with each new structure, the universe became messier, more disordered. This relentless climb of entropy isn't just a side effect of cosmic evolution, it's the engine driving time's arrow forward. The cosmic dawn marked a pivotal moment in this story. Before the first stars, the universe was a relatively simple place, a fog of hydrogen and helium, gently stirred by gravity. But when those stars burst to life, they didn't just illuminate the darkness, they shattered the calm. Supernova scattered heavy elements, radiation ionized vast swaths of gas, and black holes churned spacetime into chaos. Each of these events pumped entropy into the cosmos like a furnace, locking time into its irreversible march. Here's the twist: entropy doesn't just explain why time moves forward. It might also explain why the cosmic dawn happened at all. Some theories suggest that the universe's initial low entropy state was the ultimate cause of structure formation. Gravity, acting on tiny quantum fluctuations, amplified those imperfections into galaxies and stars because doing so maximized disorder. In other words, the universe lit up not despite entropy, but because of it. Yet mysteries linger. Why did the universe start in such an ordered state to begin with? Was it a fluke, or does some deeper principle dictate that time must have a clear direction? The cosmic dawn offers a unique testing ground. By studying how entropy changed during reionization, we might uncover whether time's arrow was inevitable, or if a universe with different initial conditions could have seen time flow backward or even sideways. The connection between cosmology and thermodynamics runs deeper than we once thought. The same forces that lit the first stars also set the clock ticking, weaving time and light into a single, unbreakable thread. And every second that passes as galaxies collide and stars burn out, the universe whispers the same lesson: chaos isn't just noise, it's the price of existence, the reason we remember yesterday but not tomorrow, and the hidden signature of a cosmos learning how to shine. To understand the universe's beginnings is to touch the very edge of human comprehension, a place where data meets wonder, where equations brush against existential awe. This isn't just astronomy, it's a mirror held up to our deepest questions. Why is there something rather than nothing? How did chaos birth order? The cosmic dawn isn't merely a chapter in a physics textbook, it's the prologue to every story that followed, including our own. Consider the audacity of this pursuit. We're creatures who live for decades, confined to a speck of dust in an unremarkable galaxy. Yet we've pieced together events that unfolded 13.8 billion years ago. We've done it by decoding the faintest whispers of light, by translating the cosmic microwave background's static into a narrative, by building digital universes inside supercomputers. This isn't just science, it's the universe becoming conscious of itself through us. But the wonder runs deeper than achievement. Every time a telescope like JWST captures light from the first galaxies, we're not just collecting data, we're bearing witness. Those photons traveled across eternity, through expanding space and swirling nebulae, just to land on a detector built by curious apes on a rocky planet. The sheer improbability of that connection humbles even the most rigorous scientists. It's why astronomers sometimes speak in near-poetic terms about their work, why phrases like time machines and light echoes pepper their papers. The cosmic dawn blurs the line between calculation and reverence. This quest also exposes a beautiful tension in how we seek truth. Science demands evidence, reproducibility, skepticism, yet the universe's origins push against those boundaries. We'll never directly observe the first stars igniting. We reconstruct them from fragments and shadows. Like detectives solving a billion-year-old cold case, we rely on forensic clues, the chemical fingerprints in ancient stars, the polarization patterns in the CMB, the distribution of galaxies like cosmic breadcrumbs. It's a reminder that understanding isn't always about seeing. Sometimes it's about listening to the silence between the notes, and then there's the existential layer. The cosmic dawn reshapes our sense of time. Human history spans milliseconds on the universe's clock. Civilizations rise and fall in the time it takes a galaxy to rotate once. Yet here we are, tracing our lineage back to those first fiery stars, their atoms now woven into our bodies. This connection collapses the distance between past and present, making the cosmic story personal. When you breathe, you inhale remnants of supernova. When you touch water, you're feeling molecules forged in interstellar clouds. Science becomes sacred when you realize you're not just studying the universe, you're its living archive. Perhaps that's the ultimate lesson of the cosmic dawn. It's not just about when light pierced the darkness, but why that story resonates so deeply. In uncovering the universe's beginnings, we're really searching for our own place in the narrative. Every observation, every theory, every late-night debate among astrophysicists is part of a much older tradition, the human need to look up and ask, where did this all come from? And in that question, science and philosophy become one. Who gets to tell the story of the universe's first light? As telescopes like JWST peel back layers of cosmic history, we're forced to confront a profound ethical dilemma, one that stretches far beyond technical challenges or scientific rivalries. The cosmic dawn isn't just data, it's a shared inheritance, a chapter of existence that predates nations, cultures, and even Earth itself. Yet access to this knowledge remains uneven, tangled in geopolitical tensions and resource disparities. Consider this: while wealthy nations launch billion-dollar observatories, researchers in developing countries often struggle for basic computing power to analyze public datasets. The irony is staggering. We're decoding the birth of a universe where all matter was once equally distributed, while replicating old patterns of inequality here on Earth. The problem isn't just funding, it's infrastructure. Raw data from space telescopes is technically available to anyone, but turning those numbers into discoveries requires supercomputers, specialized software, and trained teams. It's like handing someone the ingredients for a gourmet meal without utensils or a kitchen. Projects like the African VLBI network are challenging this imbalance by building radio telescopes across the continent, empowering local scientists to study cosmic dawn signals without relying on foreign institutions. These efforts reveal a truth often overlooked. Equity in astronomy isn't about charity, it's about unlocking perspectives. When researchers from diverse backgrounds engage with the same data, they ask different questions, spot overlooked patterns, and ultimately enrich humanity's collective understanding. Then there's the question of cultural sovereignty. Indigenous cosmologies from Aboriginal Dreamtime to Navajo star knowledge have described cosmic origins for millennia, often with uncanny parallels to modern astrophysics. As Western science discovers the cosmic dawn, how do we honor these ancestral frameworks without appropriation? Some observatories, like Chile's ALMA, now collaborate closely with local communities, blending traditional sky knowledge with cutting-edge research. These partnerships remind us that the universe's story has always been plural, narrated through countless lenses long before Hubble or JWST gazed upward. The stakes extend beyond academia. Space archaeology, a fledgling field, already debates who should govern artifacts like Apollo landing sites or defunct satellites. As we uncover the universe's primal history, could we face claims over first discovery, rights to ancient cosmic events? It sounds speculative, but legal scholars point to precedents like the 1967 Outer Space Treaty, which declared celestial bodies the province of all mankind. Applying this ethos to cosmic dawn research means treating insights about the first stars not as property, but as a commons, a living library where access isn't gatekept by patents or paywalls. Perhaps the most urgent ethical frontier lies in AI's role. Machine learning now sifts through cosmic data, identifying patterns humans might miss. But these algorithms often inherit biases from their creators, favoring theories popular in dominant research institutions. If an AI trained primarily on Western astrophysical literature interprets the cosmic dawn through a narrow lens, could it inadvertently erase alternative interpretations? Initiatives like the Open Universe project aim to democratize AI tools, but the gap persists. The solution may lie in community peer review, where algorithms are stress-tested across global research teams to expose blind spots. This isn't just about fairness, it's about survival. Climate change and light pollution already threaten Earth's observatories, while satellite megaconstellations streak across once pristine skies. Preserving humanity's ability to study the cosmic dawn requires international cooperation on unprecedented scales, transcending borders to protect our shared window into the past. The same collaborative spirit that built the Event Horizon telescope, linking dishes across continents to image a black hole, could model how we safeguard cosmic heritage for generations who will ask their own questions of the ancient light. Ultimately, the ethics of cosmic exploration mirror the universe's own story, a tale of fragments coalescing into something greater. How we distribute knowledge, credit, and tools today will determine whether the cosmic dawn remains a monologue narrated by the privileged, or evolves into a chorus of voices as vast and varied as the galaxies themselves. The first starlight belonged to no one, and that's precisely why it should belong to everyone. The story of the universe's first light isn't just for astronomers, it's a birthright, a chapter in the grand narrative that belongs to every one of us. Think about it, the atoms in your hands, the air in your lungs, even the light hitting your eyes all trace back to that primordial dawn. But too often, cosmology gets trapped in jargon, locked behind equations that feel like a foreign language. The truth is, these discoveries aren't just academic curiosities, they're invitations to awe, to connect with something far larger than ourselves. When a child gazes at the night sky and asks, "Where did it all come from?" That's the cosmic dawn speaking through them. Science communication is the bridge between the telescope and the playground. It's not about dumbing down the universe's complexities, it's about translating wonder. Take the cosmic microwave background, for example. To a researcher, it's a dataset, a graph of temperature fluctuations. But to a classroom of students, it's the afterglow of creation, a baby picture of the universe they can hold in their imaginations. When we frame it that way, not as abstract science but as a shared origin story, suddenly, those faint microwaves become as visceral as a campfire's warmth. This isn't just about inspiration, it's about empowerment. Every time a citizen scientist classifies galaxies in a project like Galaxy Zoo, or a teenager watches a YouTube explainer on JWST latest discovery, they're not just absorbing facts, they're participating in humanity's oldest conversation. And the stakes are higher than ever. In an era of climate crises and misinformation, a society that understands how science works, how evidence builds, how theories are tested, is one better equipped to face global challenges. Cosmology, with its scale and grandeur, is a gateway to scientific literacy. The magic happens when we meet people where they are. A farmer in Kenya might not have a telescope, but they can look up at the same Milky Way that inspired Galileo. A subway rider scrolling on their phone might stumble on an animation of the first stars forming, and in that moment, the universe clicks into focus. Tools like planetarium shows, augmented reality apps, and even TikTok astrophysicists are democratizing access, turning cosmic history into something you can experience, not just study. But accessibility isn't just about platforms, it's about perspective. Indigenous astronomers remind us that Western science isn't the only way to know the stars. The Maori see the Pleiades as Matariki, a celestial signal for the new year. The Navajo speak of the cosmos as a carefully ordered tapestry. When we weave these narratives together, the story of the first light becomes richer, more inclusive, a mosaic of human curiosity. Ultimately, the cosmic dawn isn't just something we observe, it's something we inhabit. Every time we marvel at a sunset, every time we feel small under a starry sky, we're touching that ancient legacy. And when we share that wonder, whether through a viral video, a museum exhibit, or a bedtime story, we're passing on a torch lit 13 billion years ago. The universe didn't just wake up once. It wakes up every time someone looks up and asks, what else is out there? For all we've uncovered about the cosmic dawn, the universe still guards its deepest secrets with relentless silence. Take that mysterious gap, the so-called Dark Ages stretching hundreds of millions of years between the Big Bang's fading echo and the first starlight. Why did it take so long? The leading theory points to temperature. The universe needed to cool enough for hydrogen atoms to clump under gravity's pull. But recent simulations reveal a twist. Those early gas clouds might have been bombarded by leftover heat from the Big Bang, a relentless cosmic microwave background that kept hydrogen just slightly too warm to collapse easily. It's like trying to form ice cubes in a lukewarm drink. Some researchers even speculate that dark matter played a role, its peculiar gravitational nudges either accelerating or delaying star formation in ways we're only starting to model. Then there's the black hole enigma. Supermassive black holes weighing billions of suns existed when the universe was less than 1 billion years old, an impossible growth spurt by today's standards. How one radical idea suggests direct collapse black holes, where enormous gas clouds skip the star stage entirely, imploding straight into black holes under their own weight. Others propose a runaway chain reaction, early black holes gorging on dense primordial gas at rates that would choke their modern counterparts. The wildest theories invoke primordial black holes, relics from the Big Bang itself, seeding the cosmos with ready-made monsters. But here's the catch. No model perfectly explains the sheer size of those early behemoths without breaking our understanding of physics. These aren't just academic puzzles, they're cosmic breadcrumbs. Each unsolved mystery forces us to question fundamental assumptions. If dark matter interacts differently than we think, or if gravity behaves oddly at extreme scales, the answers could rewrite textbooks. Upcoming telescopes like the Einstein probe and LISA will hunt for clues in gravitational waves and X-rays, while quantum computers may simulate conditions no supercomputer can handle. Perhaps the most humbling truth is this: every discovery about the cosmic dawn seems to birth two new questions. But that's the beauty of exploration. The universe isn't a puzzle to be solved, but a conversation that never ends. And with each generation of tools, we learn to listen a little better. The cosmic dawn isn't just a chapter in our past, it's a gateway to the universe's greatest mysteries, each one branching into questions that could redefine reality itself. Consider quantum gravity, the holy grail of modern physics. The first moments after the Big Bang, when the universe was smaller than an atom, demand a theory that marries Einstein's relativity with quantum mechanics. Those primordial instants set the stage for everything that followed: the distribution of matter, the birth of the first stars, even the arrow of time. By studying the cosmic dawn's aftermath, we're reverse engineering clues about conditions so extreme they defy our current laws of physics. Gravitational waves from merging black holes might carry echoes of quantum fluctuations from that era, while anomalies in the cosmic microwave background could reveal spacetime's granular nature. It's like finding cracks in a fresco and realizing they trace back to the brushstrokes of creation. Then there's the enigma of dark matter and dark energy, the twin shadows that shape the cosmos. The cosmic dawn's timeline holds vital clues about how dark matter behaved in the early universe. Did it interact with itself, slowing galaxy formation? Or did it clump faster than models predict, explaining why JWST sees mature galaxies too soon? Future experiments like the Vera Rubin Observatory will map billions of galaxies, searching for patterns that could expose dark matter's identity, whether it's undiscovered particles, primordial black holes, or something even stranger. Meanwhile, dark energy's potential early activity during reionization might explain why the universe's expansion is accelerating. These aren't abstract puzzles. They're keys to understanding whether the cosmos will expand forever, collapse, or tear itself apart. Life's origins intertwine with this story too. The heavy elements forged by the first stars, carbon, oxygen, iron, became the raw materials for planets and biology. But could life have arisen even earlier, in exotic environments around population Roman 3 stars? Their intense ultraviolet radiation might have sterilized nearby space, but tidal forces on moons or deep in gas giants could have offered sheltered oases. Astrobiologists now speculate about hyper-advanced civilizations that might have emerged billions of years before Earth formed. If such beings harnessed the energy of their young, volatile galaxies, could relics of their technology, or even their descendants, still linger in the cosmos? SETI's search for alien signals is expanding to include technosignatures from these ancient epochs, like industrial pollution in exoplanet atmospheres or Dyson spheres built around white dwarfs. The tools we'll use to explore these frontiers sound like science fiction. Quantum sensors could detect dark matter particles by their minuscule gravitational tugs. Neutrino observatories might catch particles from the universe's first seconds, buried under mountains to shield from interference. And telescopes like the proposed Habitable Worlds Observatory aim to directly image Earth like exoplanets, analyzing their atmospheres for signs of life. Meanwhile, breakthroughs in artificial intelligence are revolutionizing how we interpret data, with neural networks spotting patterns in cosmic noise that human eyes would miss. But the most profound revelation might be philosophical. The cosmic dawn forces us to confront our place in a universe where time stretches backward and forward beyond comprehension. Those first stars didn't just light up the cosmos, they set in motion a chain of events that led to galaxies, planets, and life forms capable of wondering about their origins. In tracing that journey, we're not just uncovering history, we're participating in it. Every observation, every theory, every late-night debate among scientists is part of the universe's growing self-awareness, a story that began with light and continues with us. The adventure is just beginning. With each new discovery, we're not only answering old questions, we're learning how to ask better ones. And somewhere out there, in the faint glow of those first stars, the next great mystery is waiting. The story of the universe's first light isn't just a record of ancient events, it's a mirror reflecting our deepest connections to the cosmos. Every element in your body, every spark of energy fueling your thoughts, traces back to those primordial moments when darkness first gave way to dawn. This isn't abstract science, it's genealogy written in starlight. The iron in your blood was forged in the hearts of exploding stars. The calcium in your bones was scattered across space by supernova. Even the oxygen you breathe is a gift from generations of stars that lived and died before our solar system existed. You are, quite literally, the universe's way of remembering itself. But the cosmic dawn's significance runs deeper than chemistry. It challenges us to rethink our place in time. Imagine the entire history of the universe compressed into a single year. The Big Bang striking at midnight on January 1st, galaxies forming by spring, our sun igniting in late summer. On this scale, all of human civilization occupies less than the final second of December 31st. Yet here we are, in that fleeting instant, reconstructing events from the universe's first days with astonishing precision. There's something profoundly humbling. and exhilarating about creatures who live for decades deciphering a story 13.8 billion years in the making. What makes this exploration so urgent isn't just the answers we've found, but the questions that keep unfolding. Every breakthrough peels back another layer, revealing deeper mysteries. The James Webb Space Telescope's discoveries have upended our timelines, showing galaxies growing too fast, black holes growing too large. These anomalies aren't failures, they're guideposts pointing toward physics we haven't yet imagined. Perhaps dark matter interacts in ways we've missed. Maybe the early universe hosted exotic particles long since vanished. Or could there be entirely new forces at play, their traces etched into the cosmic microwave background? The cosmic dawn isn't a solved puzzle. It's a living conversation, one that reshapes our understanding with every observation. This journey also reminds us that science is a collective endeavor. The cosmic dawn wasn't uncovered by a lone genius, but by generations of astronomers, engineers, and dreamers, from the theorists who first calculated the Big Bang's afterglow to the technicians who painstakingly aligned JWST mirrors in the vacuum of space. It's a story of collaboration across cultures and continents, of telescopes on remote mountaintops and algorithms sifting through petabytes of data. When we marvel at an image of a distant galaxy, we're witnessing the culmination of countless hours of labor, curiosity, and perseverance. Most of all, the cosmic dawn invites awe, not the passive kind, but the awe that sparks curiosity, the kind that makes a child point to the night sky and ask, "What's out there?" That simple question has propelled humanity's greatest discoveries, from Galileo's telescope to the Voyager probes drifting beyond our solar system. It's the same wonder that now drives us to build ever more powerful observatories, to simulate the universe's birth in supercomputers, to launch missions that will outlive their creators. As we stand at this crossroads between knowledge and mystery, one truth becomes clear: the universe's first light wasn't just an event. It was the opening note of a symphony still playing, a story still being written, and we're part of it. Every time you look up at the stars, you're not just observing history, you're continuing it. So let's keep asking, keep exploring, keep reaching for the next revelation. Because the cosmic dawn isn't just where we came from, it's where